we were discussing about second translation theorem, right? I would recall what we did. Second translation theorem. But this says that Laplace transform of f t minus a times u t minus a equal to e to the translation theorem e to the minus s and plus. Okay, this is what second translation theorem says. Okay, and what is the first translation theorem? It says that if you do multiplication in the time domain, that is, if you multiply by exponential in the time domain, that would result in translation in the Laplace domain. Okay? So first translation theorem says something about multiplication by exponential in time domain, and that would result in translation in the Laplace domain. And so in the second translation theorem, it states that translation in the time domain would result in multiplication by exponential in the Laplace domain. Okay, so these two tools are very important, right? These two are very powerful tools, right? So my first example, that's from second translation theorem. Can you give a try for this problem? I would sketch a graph. This is my t-axis. Suppose we have something like this. This is 1, this is 3. Five, 3, 2, 1. Okay, this is function ft. And my problem is find the Laplace transform of ft. This is my problem. Okay, can you give a try? I have given you a function. You need to find the Laplace transform of this function. Use second translation theorem. Let's try to write this function as a combination of the step function. Right? That's what we did in our last class, right? Let's write down this as a combination of the step functions. So recall what is Laplace transform of ut. What is our definition of ut? Ut is 1 if t is positive, and ut is 0 if t is negative. Okay, and Laplace transform of ut is equal to 1 divided by s. Okay. Use these tools and try to evaluate the Laplace transform of this function. Okay. So how do you express this function? Did anyone express this function as a combination of the step functions? How do you express this? Let's think about this first piece.
Okay, like the first one, 5. I did it with 5 and then it's t minus 1, but it's in brackets. Excuse me, I didn't close it further. I did 5 first on the top line.
Yeah.
So that one right there, I just did 3 because it's only
So
going
3
from-
times what? So how do you represent this line segment? So let's think about this first
T
line
minus
segment.
1.
It's ut minus ut minus.
Okay.
Okay. So what is 3 times ut? Then that is this line, right? So this line segment is, so what is ft? Ft equals 3 times ut minus 1. Because I need only this region, right? So if I multiply 3 by ut minus 1, I would get this line segment. Okay. Then how would you get this line segment? That is plus 5 times. Now, what is 5 times ut minus 1? Ut minus 1 starts at 1 and it would go to infinity, right? So if I subtract ut minus 2 from ut minus 1, I would get this line segment. Okay. Then 3 times ut minus 2 minus ut minus 3. Okay. Sorry, 1 times because the value is function value is 1. You consider this line. Right. Any questions about that idea? So remember this, that's very important, right? So so the idea is, suppose you have some graph like this. It's from A to B, and this value is lambda, right? So what is the equation of this graph? It is equal to lambda times ut minus A minus ut minus B. Okay. If I subtract ut minus B from ut minus A, I would get this line segment. I'm multiplying by lambda because my value is lambda. Okay. Right. So this is my function. Now it's easy to evaluate the Laplace transform. Right. So how do I evaluate the Laplace transform? So first I would count what are ut minus 1, right? So if t equals 3 times ut. Now I have 5 times ut minus 1, negative 3 u times ut minus 1, that means 2 times ut minus 1 minus 5 times ut minus 2 plus ut minus 2, that means minus 4 ut minus 2 and minus ut minus 3. Okay, this is my function. Okay, minus 5 plus 1 minus 4, right? Okay, any questions about this one? Right. Now we know what is the function. So this is the most difficult part in this theorem, right? So if you get some problem related to certain translation theorem, the representation of the function is the hardest part, right? After you represented the function, then you can directly apply the second translation theorem, right? So what is my ft? My ft is going to be equal to 3 times ut plus 2 times ut minus 1 minus 4 times ut minus 2 minus u times ut minus 3. Okay. Right. Now let's consider the Laplace transform of this function. Okay. I can apply the linearity, right? I have summation of some functions. So by the linearity, this is equal to Laplace transform of ut plus 2 times Laplace transform of ut minus 1 minus 4 times Laplace transform of ut minus 2 minus Laplace transform of ut minus 3. Right? Okay. Now what is the Laplace transform of ut?
One of us,
1 over s. I will get 3 times 1 over s plus 2 times. What is the Laplace transform of ut minus 1? Now it is a translation, right? This is actually 1 times ut minus 1. Okay, translate. So by the second translation theorem, I can write e to the minus 1 times s times Laplace transform of ut. Okay. Now what is the Laplace transform of this one? That is minus 4 e to the minus 2s Laplace transform of ut. Okay. And you can see to the next one, it is e to the minus 3s Laplace transform of ut. Okay. Right. So Laplace transform of ut is 1 over s. So I would insert that. So I would get 3 divided by s plus 2 times e to the minus s divided by s, because Laplace of ut is again 1 over s, minus 4 e to the minus 2s divided by s minus e to the minus 3s divided by s. Okay. So now we can see that the second translation theorem is very powerful, right? It's powerful than the first translation theorem, right? So again, remember what is the Laplace transform of second translation theorem, right? So you have t minus a ut minus a that is equal to e to the minus a times fs, that means Laplace transform of ft. Okay. This is what second translation theorem is. Okay. Any questions about? My next example is find inverse Laplace transform of 2 times e to the minus 3s divided by s plus 1 to the power 2 plus 4. So in this case, you have to apply both of them. You have to apply first translation theorem as well as the second translation theorem. Because e to the minus 3s is appearing. That means, so in the Laplace domain, you would see some exponential. What does that mean? That means you might get multiplication by exponential in the or translation in the time domain. Okay, because in the Laplace domain you have some multiplication by an exponential, right? So you would get a translation in the time domain, right? Let's think about this, right? First, you can apply the linearity and you can take this 2 out. Okay. Inverse 2 times e to the minus 3s divided by s plus 1 to the power 2 plus 4. First, I would take 2 out. Okay. Right. Now let's think about the exponential.
You can't take the explanation out?
You cannot take.
You can?
Yeah.
You can or can't?
Can't.
Can't.
Because it depends on s, right? You can take any constant out, right? Right. So let's think in this way. Let's forget exponential and forget this plus 1, right? So what can you say about the Laplace transform of 2 divided by s square plus 2 square? That's how you inverse Laplace of this function.
It'll be sine -2.
Sine 2t. Because instead of omega we have 2, this is kind of omega divided by s square plus omega square, right? So this is sine 2t. Is that clear? Right. Let's begin from this one and let's go on until we reach this expression. Right? Okay. Next, I would do something like this. Next, what can you say about? So this is the inverse Laplace transform of this one. In the other way, Laplace transform of sine 2t ut is equal to 2 divided by s square plus 2 square, right? So therefore, usually we write these pairs in this way: sine 2t ut is 2 divided by s square plus 2 square. That means the Laplace transform of this function is this one. Inverse Laplace of this one is this one, right? So we are using these double arrows to represent that. Okay, right. Now I can see this s plus 1. Okay, so I would do multiplication by e to the minus t. So what is the Laplace transform of e to the minus t sine 2t ut? Now I multiply it by e to the minus t in the time domain. So what would happen in the Laplace domain? Yes, you would get translation, right? So what is the translation? S would become s minus minus. Okay. So if you take the Laplace transform of this function, you would get a translation in the Laplace domain, that is s plus 1 to the power 2 plus 2 square. Okay. Right. This is from the first translation theorem. Now we are here, right? So now the only missing part is this exponential. Okay. Right. Any questions so far? This came from first translation theorem, right? So first I figured out that these two are Laplace pairs, right? Because if you take the Laplace transform of this one, you would get this one, and if you take the inverse Laplace of this one, you would get this function. Okay. Then I saw that if I multiplied my left hand side of my time domain function by e to the minus t, I would get translation in the Laplace domain. Right. Now, the only missing part is that exponential in the Laplace domain. So, what would happen if you do multiplication in Laplace domain? That would result translation in time domain. Okay, right. So, now I am going to multiply this function by e to the minus 3, yes? So, what would happen in the Laplace domain? T would become t minus 3. Okay, so sine root t minus 3 u t minus 3. Okay, right. So actually we do not need this 2. Take this 2 out, right? So now we have inverse Laplace of this function, right? So what is the inverse Laplace of given function? Is this one. Okay. So it is equal to e to the minus t minus 3 sine 2 times t minus 3 u t minus 3. Okay. So in this problem, I used first translation theorem and second translation theorem. Okay. So if you see translation in the Laplace domain, that means you have to do multiplication by an exponential in the time domain. And if you see an exponential in the Laplace domain, that means you have to do translation in the time domain. Okay. So those two ideas are very, very important, right? First and second translation theorems. Any questions about this? So I'll do another one example. Yes. That is the inverse Laplace of 4 times e to the minus s divided by s square minus 6s plus 25. Right? Can you try to find the inverse Laplace transform of this one? You have to use the completing square method. So I will show how to do completing square. You have s square minus 6 times s plus 25. This is equal to s minus divide this minus 6 by 2, then you would get minus 3. S minus 3 square plus 25, then subtract the square of this negative 3. Okay, what is 25 minus 9? That is 16. So in the denominator, you have this expression s minus 3 to the power 2 plus 4 square. Okay, right. Then apply the same principles that I used. Right. Try to start from the easiest one and continue. And final exam is completely from Laplace transforms. Right. Mainly from first translation theorem, second translation theorem, and idea of linearity, convolution, and delta function. Right. Most probably I would start convolution on tomorrow.
How many
And-
questions do you think it's gonna be?
6. It is kind of similar to mid exam. You have 6 questions and that means one of them is extra credit.
You said it starts with what? In cost? The questions are, the questions covered, which one are you talking about?
Laplace transform, first translation theorem, second translation theorem, convolution, delta function. Those 4 key ideas. Right. This is what you have, right? Completed the sky in the denominator. I have a quadratic in my denominator, so I completed the square. Okay. So how do you start? So as I did in the previous example, forget exponential, forget this minus here. Right? Consider 4 divided by s square plus 4 square. Right? So what can you say about 4 divided by s square plus 4 square? What is the inverse Laplace transform of this one?
Sine 4t minus 5,
Sin 40 ut.
t minus 5. No, not minus 5, it's
Sin 40 ut, right? Because this is, you do not have exponential here. Yes. So you get only sin 40 ut. Right? Right. Then, in the original case, I can see translation in the Laplace term. So what would I do? I would insert exponential in the time term. So I would multiply by e to the 3t in the time term. That would give the translation in the Laplace domain. So I would get 4 divided by s minus 3 to the power 2 plus 4 square. Okay. Right. Now what is the only missing part? That is the exponential in the Laplace domain. So if I need an exponential in the Laplace domain, what can I do? I need an exponential in the Laplace domain. So I can apply translation in the time domain. Okay. So the exponential that is appearing is e to the minus s. Right? That means minus s means minus 1 times s. So I have to do translation by 1 unit in time domain. Okay. So 1 sine 4 times t minus 1 ut minus 1. The inverse Laplace of 4 times e to the minus s divided by s minus 3 square plus 4 square. Okay. Any questions? What do you think about first translation theorem and second translation theorem? Are they hard? I think this kind of examples are not hard, right? But problems might be hard if you get some graphs like I did previously, right? Then you have to express the graph as a combination of step functions. That is the hardest part. Okay, right. Do I need to do another example of this type, or shall I move on? What do you think about this type? Is that
One
okay?
more. One more.
Let's do one. So let's think about this function. Plus of 4 times s e to the 3s divided by plus 2s. Okay. In this case, I can take 4 out, right? But it does not matter, right? So, right. Again, the first step is complete this kind denominator. So what would I get? This is the inverse, right? Laplace inverse. Laplace inverse 4s e to the 3s. I can write the denominator in this s plus 1 to the power 2 plus 2 minus 1. Okay. That means I have inverse Laplace of 4 times s times e to the minus s divided by s plus 1 to the power 2 plus 1. Okay. Right. Okay. What should I consider first? What terms can I forget? At the initial step, what should I do? I can forget exponential, right? And I would forget this plus 1, right? So I would consider only s divided by s square plus 1. Because I know the inverse Laplace transform is that. Okay. So what can you say about s divided by s square plus 1 square? What is the inverse Laplace transform of this function?
Cosine.
Cosine, right? It is cosine t ut. Okay. Right. Now let's try to construct this translation in Laplace domain. Okay. So if you consider the Laplace domain, you have s plus 1 to the power 2. So translation has been applied in the Laplace domain. Okay. So what can I say about the inverse Laplace of s divided by s plus 1? That means s minus 1 square plus. What is the exponential that I need to multiply in the time domain? I have s minus a square. A is minus 1. So you need to multiply by e to the minus t in the time domain. Okay. So minus t cosine t ut. Okay. Right. Right. Now we are okay with the denominator, and the only missing part is this exponential. Right. So exponential is appearing in the Laplace domain. So what should I do in the time domain? Translation. Right. Okay. So s times e to the minus s in the Laplace domain. That means I have to apply translation by 1 e to the 3s, right? Oh, sorry. 3s. Okay, so what is the translation that I need to apply? In the time domain?
Then also go to that, e to the negative t is also 3, or,
No, it is negative two, because it came from here, right?
oh, okay.
Due to this translation. So now I have to care about this e to the 3s, right? So what can you say? If e to the minus as would appear in the Laplace domain, the translation is by minus a, right? That means, for example, in this case, e to the minus s appeared, so I translated by 1. Okay. Now instead of, in this case, we have minus 1. Now what would we have in this case? Plus 3. Right? So what would become t? T would become e to the minus t plus 3. Cosine t plus 3 ut plus 3. Is that clear? So formulas are going to be behave differently in these two theorems, right? In the first translation theorem, it behaves in a different way, and in second translation theorem, it behaves in another way. Because if you have minus 1, you have to put minus 1 in the second translation theorem. Right? So now I have 4 here, right? So I put multiply both sides by 4. Okay. So then this function is the inverse Laplace transform of this. Okay. Any questions about this? How I got these translations? Questions? Is it hard to determine this?
It's just tedious,
Yeah.
like little things you can mess up.
Yeah. Yeah. The trickiest thing is those difference, right? So in the first translation theorem, it says that the translation theorem says this, right? Laplace e to at ft is equal to fs minus a. So this a would become minus a when you go to the Laplace term, right? But second translation theorem would say ft minus a ut minus a is equal to e to the minus a. So if you have minus a, you would get minus a. Right? And reverse. Okay. Let's do some more examples, right? On these two theorems. So let's consider this one. Laplace transform of t times e to the minus 6t. ut. What can you say about this one? Now, what has happened in the time domain? Multiplication by an exponential. Okay. So, what would happen in the Laplace domain? Translation, right? So, let's think in this way. So, what is the Laplace transform of t? What is the Laplace transform of t?
And to the
1 divided by s square.
plus
Right? Now we are multiplying by e to the minus 60. Okay? Minus 60 TUT. Okay, now instead of a, I have what? Instead of a, I have minus 6. Okay, instead of a, I have minus 6. So, what would be the what would happen to the Laplace transform? My fs is, in this case, fs is 1 over s square. Okay, fs is 1 over s square. This is the Laplace transform of original function, right? And I am multiplying by e to the minus 60. Okay, so what is the Laplace transform of that? Okay. Instead of a, I would plug minus 6. So what is that? F is plus 6. It is equal to 1 divided by s plus 6 square. Okay. So this would be s plus 6 square. Okay. Is that clear? I would get a translation in the Laplace domain. I had 1 over s square. This is my Laplace transform. It would be translated by minus 6. Okay. Any questions about this one? It is easy, right? Okay, let's move into the next example. The Laplace transform of t minus 1 square e to the 2t ut. How do you find the Laplace transform of this one? We don't know what is the Laplace transform of t minus 1 square, right? So first I would expand this. What is that? T square minus 2 times t plus 1 e to the 2t. Okay. Laplace of t square e to the 2t ut minus 2t e to the 2t ut plus e to the 2t ut. Okay. Now I can apply the linearity, right? Because I have summation of 3 functions, right? Then I would apply the linearity. So by the linearity, I have Laplace of t square e to the 2t ut minus 2 times Laplace of t e to the 2t t plus Laplace of e to the 2t ut. Okay. Right. Then we have to do the same thing, right? What is the Laplace transform of t square times e to the 2t? Okay, forget about e to the 2t.
1 over s cubed,
What
or just t
square
squared?
t square, it is 2 over s cube.
Oh,
Because what is the Laplace transform?
yeah. Okay.
Laplace transform of t n is factorial n divided by s to the power n plus 1. Okay. So Laplace transform of t square is 2 divided by s to the power 3. Right. Now I have multiplied that by e to the 2t. So what would happen to that Laplace transform? It would get translated by 2 units. Okay. So if you have this original function, then the Laplace transform is 2 divided by s to the power 3. Now instead, because of this exponential, it would be translated by 2 units. So it would be s minus 2 to the power 3. Okay. If I don't have this e to the 2t, I would get only s, right? But due to this 2, I get translation by 2 units. Okay. Because here I am having 2, right? That's why I get s minus 2. Here I had a negative now. That's why I got positive. Okay. That part is done. Now what can you say about the next one? Laplace of t is 1 divided by s square. Again, it would be translated by 2 units because I am multiplying that by e to the 2t. Okay. So I will get 1 divided by s minus 2. Right?
Then you put the 2 back in.
Yeah, 2. Yeah. 2 times. Yeah. 2 times. Sorry. The final portion. Okay. If I don't have e to the 2t, I have only ut. Laplace of ut is 1 divided by s, right? And I have multiplied that by e to the 2t. So the Laplace domain would be translated. That means that will become s minus 2. Okay. Any questions about these 2 examples? So let's move into a different one. I will give you 2 problems. Find Laplace transform of e to the 2 1 and evaluate the Laplace transforms of these four functions. Use second translation theorem. You can take 4-minute break and continue, right? What do you think about the first one? Third problem.
The third problem?
This one? How do you relate second translation theorem to this problem? To apply second translation theorem, we need the same number in these two positions. Right? Because second translation theorem says this Laplace of ft minus a ut minus a is equal to e to the minus as Laplace of fs. Okay. This is what second translation theorem says, right? But here we have e to the 2 t minus 1 and t minus 3. Okay. If I have t minus 3 here, then I can apply second translation theorem. Okay. So I would make this 1 into 3. So let's do something. Let's do some algebraic trick, right? So I need the Laplace of e to the 2 t minus 1 u t minus 3 equal to Laplace of, so this is what I am doing. I would subtract 2 and add those two. Okay. The minus 1 minus 2 plus 2. Right. So I did not do anything to original expression. Right. Yes. Still I am having t minus 1. Okay. Right. Times ut minus 3. Is that step clear? I rewrote this t minus 1 in this form. Right. Now I would combine these two terms. So I would get Laplace of e to the 2 t minus 3 plus 2. Still I am having t minus 1, right? Times ut minus 3. Then I would apply the rules of exponentials. Right? I can write this function in this form. E to the 2 t minus 3 plus 4. That means I can decompose that in this way. Is that clear? Okay. So I have e to the 2 times t minus 3 plus 2 times 2 ut minus 3. Right. Now e to the power 4 is a constant. Right? E to the power 4 is a constant. I would take that out. E to the 2 t minus 3 u t minus 3. Now I am done. Right? Because now I have something like this ft minus a ut minus a. Now what is my a? What is my a? Instead of a I have 3, right?
Oh, yeah.
T minus a 3. So what would be my Laplace transform? Get e to the power 4 times e to the minus a is 3s times Laplace of my original function. What is my function? E to the 2t, right? That's my original function. Now what is the Laplace of e to the 2t? It's 1 divided by s minus 2. Okay. We have e to the power 4, e to the power minus 3s divided by s minus 2. Because we proved that Laplace of e to the at is 1 divided by s minus a. Right? I used that fact. This is another good problem from second translation theory. Fine. Any questions about this example? Right. Next, we would move into this one. It is trivial, right? Because now you have same thing in the both of them. Right? T plus pi over 6, T plus pi over 6. Now, for this problem, you can directly apply second translation theorem. Okay. Shall I erase this portion? So how do you do the fourth problem? Fourth problem is find the Laplace of sine T plus pi over 6 u T plus pi over 6. Now, in this case, there would be no any problems, right? Because in this case, the problem was here I had t minus 1 and here I had t minus 3, right? So how do you find this? So instead of a, what would you have in this problem? Negative pi over 6, right? So Laplace transform is going to be e to the negative pi over 6 times the Laplace transform of original function, that is sine t. Okay. What is the Laplace of sine t? S pi over 6, s right to the as times Laplace of sine t. What is the Laplace of sine t? That is 1 divided by square plus 1. Right. You can use tables for them, right? You do not need to memorize e to the pi over 6. Right. Okay. Definition, right? Instead of a, I had negative pi over 6. So instead of a, I plug negative pi over 6. That's what I did, right? Now can you try fifth problem? It's another good one, right? Because now you can see here you have t and here you have t minus pi over 6, right? Can you do problem number 5? How do you find this one? We have to make that t to t minus pi over 6. That's the trick, right? So how do you make that?
Pi over six minus pi over six.
Yeah, same trick that I used. Yeah. Let's insert that. So I have sine t instead of t, I would write t minus pi over 6 plus pi over 6 times ut minus pi over 6. Okay, right. Then I would consider this t minus pi over 6 as one number, right? So then I would use this rule. From trigonometry, we know that sine a plus b. What is sine a plus b? That is equal to sine a cosine b plus cosine a sine. Sine a cosine b plus cosine a sine of b. Then I would use this rule. Okay? Right. Now this is t minus pi over 6 is kind of a and pi over 6 is b. Okay. So I would expand this in this sine t minus pi over 6 cosine pi over 6 plus cosine t minus pi over 6 sine pi over 6 times ut. Right. Any questions so far? This is A, this is B, sine A cosine B plus cosine A sine B. Okay. Now I know the value of cosine pi over 6. That is cosine 30 degrees. It is the square root of 3 divided by 2. So I could get Laplace transform of sine t minus pi over 6. Cosine pi over 6 is the square root of 3 divided by 2. And plus sine pi over 6 is 1 over 2. So 1 over 2 cosine t minus pi over 6 50. Okay. Now I would I have ut minus pi over 6, right? Ut t minus pi over 6. Okay. Right. So then I would apply linearity. Right? Before I apply linearity, I can multiply both of them by ut minus pi over 6. So what could I get? Laplace of, I can take the square root of 3 divided by 2 out, then I would get Laplace of sine t minus pi over 6 times ut minus pi over 6 plus Laplace of cosine t minus pi over 6 ut minus pi over 6. Right? Okay. Any questions so far? And here I would get 1 over 2, right? That's my constant, 1 over 2. I apply the formula for sin A plus B and I simplify it, right? Right. Now I can apply second translation theorem, right? Because now I have sin t minus pi over 6, ut minus pi over 6, cosine t minus pi over 6, ut minus pi over 6. That means instead of A, I have pi over 6. For the first piece, I would get square root of 3 divided by 2 e to the pi over 6 s Laplace of original function, that is sin t. Okay. And then for the next one, I would get 1 over 2 e to the pi over 6 s Laplace of cosine t. Any questions about my simplification? Let me know if you have any questions. Is it clear how I applied this second translation theorem? Now, what is the Laplace of sin t? It is 1 divided by s square plus 1, and Laplace of cosine t is s divided by 1 plus y square plus 1. Right? So that means I'm done. So I would write the answer in the here. So what is my final answer? It's going to be square root of 3 divided by 2 e to the, it should be minus, right? Because instead of a, I have pi over 6. It is minus pi over 6 s times pi over 6 times s. Laplace of sin t is 1 divided by s square plus 1 plus 1 over 2 e to the minus pi over 6 times s, and Laplace of cosine is s divided by s square plus 1. Okay. This is kind of tricky problem. That means it involves some computations. If you have any questions, you can ask. I can explain that again. You need. I think up to this, it's trigonometry. Then I multiplied these two terms by ut minus pi over 6 and I applied linearity. Then I can take the square root of 3 divided by 2 out, and also I can take 1 over 2 out. Right? Then I applied second translation theorem, right? Because I have sin t minus a, ut minus a. Instead of a, I had pi over 6. So instead of a, I plugged pi over 6. That's how I got this negative pi over 6. Okay. Okay, let's go into the final one. Sixth problem. That would be easier than this. Okay. I need to find the Laplace transform of t times ut minus ut minus 4. Okay. Right. Again, I would multiply, I would simplify this inside the bracket. So what would I have? The Laplace of t times ut minus t times ut minus 4. Okay. Right. Now I can apply linearity. Okay. So what would I get? Laplace of t times ut minus Laplace of t times ut minus 4. Okay. Right. Now after we reach this point, we can write down the Laplace of this term. It's easy. What is the Laplace of t times ut?
T over S. No,
1 over, yeah, 1 over square. So I have 1 over square. Right. Now the problematic part is this one. If I have t minus 4 instead of t, I can apply second translation theorem. But the problem is I have t. So I use the same technique again. So I would replace t by t minus 4 plus 4 ut minus 4. Okay. Right. So get 1 over square minus Laplace. Now I would decompose this. I would consider t minus 4 as one term and 4 as the other term. So if I decompose this, I would get t minus 4 ut minus 4 plus 4 times ut minus 4. Okay. Right. Any questions so far? Now, again, I would apply linearity. Right? Again, I would apply linearity. So I would get 1 over square minus Laplace of t minus 4 ut minus 4 minus 4 times Laplace of ut minus 4. Okay. Erase this part. Right. Now, what is the Laplace of this portion? Now you have t minus a, ut minus a. Now t has been translated by 4 units. Okay. So the Laplace transform of t is 1 over s square. So what would happen to that? That would be multiplied by e to the minus 4s. Okay. Because translation in time domain would result in multiplication by an exponential in Laplace domain divided by s square. Okay. Because my original function was t and Laplace transform of t is 1 over s square. Since I am translating my function in the time domain, I would get this exponential. Okay. Then again, here I have 1, right? Translation of 1 is also 1, right? So what can I say about this one? Right. Ut has been translated to ut minus 4. So the Laplace transform of this would be e to the minus 4s divided by s. Okay. In this case, the original function is 1. Laplace of 1 is 1 over s, and it has been translated by 4 units. Okay. Right. So this is my final answer. Right. Okay. Any questions?
you need a 4, the whole 4?
Yeah. It's 4. Nothing would happen to stay there. Okay. Any questions? Because next I would move into some another complicated examples, right? Right. So my next example is, it's a real good example. So I would give you some periodic signal, right? Suppose you have some pattern lines, 1A, 2A, 3A. Then OA, 5A. Like that, this would be continued. This pattern would be continued. Okay. First block, second block, and the width would be same, right? A, 2A to 3, 0 to A, 2A to 3A, 4A to 5A, right? These type of signals are used in electrical engineering. There's something called pulse width modulation. In communication theories, these things are used. Right, okay. This pattern is continued. So the next, this guy would start at 6A, 6A to 7A. Okay. Right. And the amplitude is 1. Right. Okay. Suppose this is your function ft. My problem is find the Laplace transform of ft. Right. My problem is find Laplace transform of this signal. And this would go to infinity, right? You do not have only finite blocks, you have infinitely many blocks like this, right? Okay. So, how would you think about this problem? Let's forget about this infinitely many blocks. First, consider only first block, right? Because each of the other squares are some translations of this first block, right? How do you construct this second square by using the first one? You have to translate this by 2A, right? If you translate this square by 2A units, you would get this one. If you translate this by 4A units, you would get this one. If you translate this by 6A units, you would get the next one, right? So let's think about the first one, right? So first, we think about the following, right? First, we would think about I would call this as GD, right? GD. We know how to find the Laplace transform of this pattern, right? How do you find the Laplace transform of this? So how do you find the Laplace transform of GT? First, you have to represent GT as a combination of the step functions. So, what is GT? It is ut minus a, right? First, we would find Laplace transform of this GT. It is easy, right? I think we did that in the previous class, but I would read you that. So, how do you find the Laplace of GT? So, what is GT? dt is equal to ut minus ut minus a. Okay? Because ut is pattern from here to infinity, and ut minus a would start at this point. So if I subtract ut minus a from ut, I would get this. Okay? Please. I would draw dotted line here, then it's clear, right? Now, what is Laplace of gt? It is Laplace of ut minus Laplace of ut minus a. Okay? By the linearity. And Laplace of ut is 1 divided by s. Right? Now, what can you say about this one? As I mentioned in the previous example, now this is the translation in the time domain. Okay, that would result in multiplication by an exponential in the Laplace domain. So you would get e to the minus a divided by s. So Laplace of gt would be 1 minus e to the minus as divided by s. Right. Right. Now let's try to write ft as a combination of gt, because now I know the Laplace of gt, right? So what can you say about ft? Now what is ft? gt is only this piece, right? What is this piece? It is t minus 2a, because you need to translate gt by 2a units to get this, right? So what is ft? It is equal to gt plus gt minus 2a plus gt minus 4a plus, like that it should be continued. Okay? Because gt is this portion, gt minus 2a is this portion, gt minus 4 is this portion, right? Okay? And using sigma notation to represent this, this is the summation from, let's say, k goes from 1 to infinity, g t minus 2ka. Okay? Because if k equals 1, I would start at 0, right? Because I need gt first. If k equals 0, I would get this term. If k equals 1, then I would get this term. K equals 2, then I would get this one, right? Okay. Now I have a summation on my right hand side, and on my left hand side I have ft. Now I would apply Laplace transform to both sides. That means then on my left hand side I would get Laplace of ft, and what would I get on my right hand side? By the linearity, on my right hand side I would get summation k goes from 0 to infinity Laplace of gt minus 2ka, right? Because I am applying Laplace to this side, Laplace to this side. So by linearity, I can write this as Laplace of gt plus Laplace of this one plus Laplace of this one, like that. Okay? Right. Now I have erased this portion. Right. Now, what can you say about Laplace of g t minus 2ka? We know the Laplace transform of gt, right? Now, gt has been translated by 2ka units. Okay, so what is the Laplace transform of g t minus 2ka? Is equal to Laplace of t equal to summation k goes from 0 to infinity. This one it is. Now, this is the translation in the time domain that would result in multiplication by an exponential in Laplace domain. So I would get e to the minus 2kas times Laplace of gt. Okay. This is the Laplace transform of original function, and it would be multiplied by an exponential. Okay. Now, what is Laplace of gt? It is independent of k, right? Laplace of gt is independent of k. So I can write this, or I can take this out of this sigma sign. Okay. So what is Laplace of gt? We found that out, right? So what would we have? Summation k goes from 0 to infinity e to the minus 2k as, and this is 1 minus e to the minus as divided by s. Okay. Then I would take this piece out of this sigma sign. 1 minus e to the minus as divided by s. Summation k goes from 0 to infinity e to the minus 2k as. Any questions so far? It's a good application of second translation theorem, right? Then I will continue. I erase that part. Right. Now I stop here. Now 1 minus e to the minus as divided by s. What is this? Now I would expand this again, right? See what this is. If you plug k equals 0, you would get e to the power 0, that is equal to 1. Okay? And if you plug k equals 1, you will get e to the minus 2 as. If you plug k equals 2, you would get e to the minus 4 as. Like that, it would be continued. Okay. And what can you say about these numbers? E to the minus a is positive, right? A is positive and s is positive, right? So these numbers are less than 1 by the properties of exponential. Right? Because e to the minus x would look like this. Right. Now, what can you say about this series from calculus 2? Consider this number is a. Then what is this? A square. Suppose this is a. Then what is this? A square. Right? Then the next term is a to the power 3. Right? So let's say a is equal to e to the minus 2 as. Not let's use some other number because A is already in our problem, right? So let's use lambda. Right, I would call lambda equals e to the minus 2as. So if this is lambda, then this is lambda square. Okay. The next term is lambda to the power 3. Right. So what would I have? 1 minus e to the minus as divided by s. 1 plus lambda square plus like that. Okay. From your knowledge in geometric series, what is this summation?
Taylor something, I can't remember the name.
Geometric series.
Yeah, I can't say.
Geometric series. So you have a geometric series and you know that lambda is less than 1. Right? Lambda is less than 1. Then this geometric series would converge. Right? You know that lambda is less than 1. So if lambda is less than 1, then geometric series would converge. And common ratio is the lambdas. Right? Okay. So what is the summation? The summation is given by first term divided by 1 minus common ratio. Right? So the summation is equal to first term, that is 1 divided by 1 minus common ratio, that is lambda. Okay. What is my lambda? It is e to the minus 2as. Okay. So 1 minus e to the minus af divided by s. 1 divided by 1 minus lambda, that is e to the minus 2as. That's my final answer. Right? So we had a periodic signal, right? And we used the Laplace transform of this portion to derive this result. Okay. So the key idea behind this computation is second translation theorem. I applied second translation theorem. Right? If you are not familiar with these ideas, again recall them, right? What is a geometric series and when does it converge? Geometric series would converge if the common ratio is less than 1. If common ratio is greater than 1, then the geometric series would diverge. And if common ratio is equal to 1, then we cannot say anything about convergence or divergence, right? Those are the 3 facts that you have to remember about geometric series. If common ratio is less than 1, then it would converge. If it is greater than 1, then it would diverge. And if it is equal to 1, then it does not say anything about convergence or divergence, right? So in this case, it's clear that lambda is less than 1 because f is my Laplace variable that is positive and a is positive here, right? So then by the graph of exponential, I can see that e to the minus 2as is less than 1. Okay. Right. So it is a good problem, right? So in tomorrow's class, I would do some more problems related to this idea. Right.
What did you say if lambda is less than 1? What did you call it?
Uh,
Greater than 1, you said it diverged. but-
diverge. If lambda is less than 1,
Yeah.
it would converge.
Converge.
In this case, lambda is the common ratio, right? Actually, it is defined for common ratio. If common ratio is less than 1, then the geometric series would converge. Right?